Welcome to my new course, Linear Algebra. I'm trying to develop this course because of its importance in mathematics. And it's a very profound and core course like calculus, for example. Of course, it's not like the first year or two of undergraduate course, but it's there, it's almost there, okay? So one has to master this course for the subsequent areas with applications, of course, in different areas. Okay, so first, before I start, in this welcome note, I want to just say a brief historical note about the development of this concept of this area, which is linear algebra, also known as matrix algebra. Okay, I will explain the keyword here is, of course, the keywords are linear and algebra. Algebra, everybody knows what it is, and we will understand why, okay? Because we do have also some linear calculus, etc., or vector calculus. So the fundamental concept that defines and captures linear algebra is the concept of vectors, okay? So vectors, they do capture this area in a very profound way. So what is the origin of vectors? Okay, the formal definition of a vector can be found, for example, with the Italian mathematician Bellavitis. Okay, in 1835. But honestly, I would say, because the concept of vector, the idea of Bellavitis is the abstract formulation of a vector. Do you understand? And not associated to anything. But the root definitely can be found with the work of Newton. And the concept that captures the vectors is the concept of force or forces. Okay, so a force is given by what? By the magnitude and the direction, and this was known to Newton. And if you look at, for example, in his fundamental second law of physics, it claims that the resultant force or the net force acting on a moving object, okay, on a moving object, which means the sum of all the forces acting on that moving object, is equal to the mass time the acceleration. So let's put R, the resultant force, equal the mass time the acceleration. So of course here the acceleration should be seen as a vector. It does not make sense, of course, in the linear motion or when you are moving on a line, but when you are moving in space, which is, by the way, the real case, we never move on a straight line. Doesn't make sense, okay, in all practical matters. Okay, so objects are moving in a spatial motion, okay, not on a straight line. In this case, what we have is we have the acceleration and the velocity are vectors, okay, and R, which is the force, and M is the mass. So as you can see, R, and this was known to Newton. So for example, if you take an object, a mass, and you attach it to, for example, three springs, or four if you want, and then what you do, you push these springs a little bit. I mean, in other words, you stretch them or you compress them and you let go, and then you will see that M is a motion, is having a motion. It's moving in a plane motion, right? Otherwise, if I wanted to make it in space, I can add more springs, and this is the case, for example, in the Manhattan Project, when you want to make the atomic bomb and you put the uranium inside the ball. Like the first atomic bomb in the Manhattan Project was spherical, and they had all these springs, and the uranium as material, which is very unstable, was put inside the center, and you have all these springs that will keep it stable. Do you understand? So when the ball was falling, it moves a little bit, the material will move. So the motion here in this case will be what? this material will be what? A space motion. And we can have also a plane motion. In this case, as you can see, we can have a plane motion, okay? And the forces, you have the recoil force. Let's say, for example, it's a plane motion. Huh? So you have here a recoil force, if it is like this, and you add them. So he knew, Newton, how to add two forces, F1 plus F2. He did investigate this, and he added two vectors. And when you look at, for example, on the right-hand side of it, the fundamental second law, you will find the mass, which is a number, time the acceleration, which is a vector. So we do have also a number time a vector. So meaning what? The fundamental properties here are what? Adding two vectors and multiplying a vector by a number. So this is the beginning of what's known as algebra, okay? So, and you do have, of course, the concept of, that's the first law, huh? If you have an acceleration which is equal to 0, okay, there's no acceleration, therefore the velocity is constant, and we have the concept of a zero vector or zero force, okay, a zero force. And we will be, of course, this is physics, huh? So this is the root of the concept of abstract vectors. Okay, so we have a structure where we find now vectors in different areas, ranging from logic programming or computer programming to economics, especially economics, by the way. So, and we'll see some examples later on with applications to economics. Another powerful tool that is captured by what? By vectors, especially when you are dealing with R2, R3, which is the plane as well as the space, the common space where we are living in. But when you go to economics, the number of variables is so big that in fact what we have is known as Rn, okay? So n being the number of entries that you are dealing with in economics. It really, n is very large. So economics is a wonderful example where the dimension we are dealing with is huge and it's big. In physics, no. I mean, we can deal with R2 if it's a plane motion or R3 if it's a space motion. But this gets complicated a lot when you go to economics. In any case, a powerful tool when dealing with this kind of linear algebra in Rn is the concept of matrices. So the concept of matrices are what's known as two-dimensional data entries, two-dimensional data entries. The tensors are what's known as three-dimensional data entries. We'll see some examples, natural examples, where matrices are a wonderful tool to use. And the major application of matrices is when dealing with systems of linear equations. So as you can see, this gives you just what? An approach or a quick idea of what linear algebra is about and what we will learn in the linear algebra. And as I said, its applications are very, very interesting. It ranges from different areas. So it's a very, very important course that one has to somehow master and take, okay? Welcome again to the linear algebra course.